All right, let's solve a few problems in this video. We'll start with considering a voltage that is defined with a complex frequency J10 and a complex constant 6 minus J8 in rectangular form, or you can convert that to prove it's true. That has a magnitude of 10 and an angle of negative 53 degrees. So let's analyze, what does it mean by that? Well, if we have one complex frequency that has an imaginary part, then we have another complex frequency that is its complex conjugate. And for that function then to be real, it must be true that the complex conjugate also exists for the complex constant. So our 6 minus J8 of K1, K2 becomes 6 plus J8. Or our 10 e to the negative j 53 degrees becomes 10 e to the positive j 53 degrees. The angles negate each other for the complex conjugate, or the imaginary parts negate each other for the complex conjugate. So we have these two complex frequencies and two complex constants associated with them. So we can say our voltage then in time domain, this is a function of t, is our K1 e to the S1t plus K2 e to the S1t. And here both S1 and S2 should be bold fonts because they are complex numbers, but they're not here. We can take our K1, we can substitute in K1 as in its polar form, and then we have our E substitute in S1. S1 was 10. And then we can, or it's J10, right? So we substitute in the J10 and substitute in K2 and S2. And then when we look at this, we have a J 53 degrees and a J 10t. So we can combine those, e to the J in parentheses, 10t minus 53 degrees plus 10 e to the negative J in parentheses 10t minus 53 degrees. And then I'm saying, well, so if we use our Euler's identity, what we have here, we have negative 53 degrees here and negative 53 degrees here. Here's our plus and minus. So using our Euler's identity, we end up with, remember, we have the 1/2 when we go in this direction, so we have to multiply by 2. So it's 20 cosine 10t negative 53 degrees. So that's, if we're given the complex constant and the complex frequency, we can come up with what that real frequency is in time domain. So this complex frequency and complex constant, we know the conjugate exists for both, and we can use our Euler's identity and complex analysis to come and take just the real part, and because the real part is just that, it's the only real part. So key here again is what we ended up with. This is equal to 2, if we analyze, that's 2 times the magnitude of our complex constant k, cosine of omega t plus theta, where theta is associated with the positive radian frequency. If we note here, S1 was positive J10, but K1 had the negative 53 degrees. So when we're given this initially, we know that that phase shift on the cosine is the negative 53 degrees. So when you're trying to decide, I've got these two complex constants, which one is associated with the phase shift of my cosine, my sinusoidal frequency, which is, we'll use the cosine because that's the real part of a Euler's identity. It's the one associated with the positive radian frequency, because really no negative radian frequency exists either, right? We can only have positive radian frequency. Right, so that's one key component of our analysis to get out of this problem. Another key component of this analysis is that we don't have any exponential damping here because sigma is equal to 0. So even though we have an exponential function, that exponential function, we're raising it to the to an imaginary number, right, to j. So that's what gives us the complex. That's our complex number. When we take the real part of that, we convert that to a sine plus a cosine, and the real part of that gives us the cosine. So those two key things, and then you know, you can verify with your Euler's identity. If we know that complex constant, the amplitude is going to be twice times the magnitude of the complex constant. All right, so let's look at a couple more examples here. Let's if we have a function in time domain, can we represent their complex frequencies in real-time functions. So we have three examples here. This is worksheet teamwork 1, which you could do along with me in this video. So if we start by looking at problem A, what we have here is the sum of two sinusoids. Both the sinusoids have the same radian frequency, but there's different exponential damping. So one thing we need to do, if you recall, with our Euler's identity, we want to convert this to a cosine. So what we have here is, we can say this is equal to 2 e to the negative 100t, and then if we convert this to a cosine, we have our cosine of 2000t. Now we have to subtract the 90 degrees, right? Because our sine lags the cosine by 90 degrees, or our cosine leads. So that's one of them. And then the other one just has a a coefficient of 1, so we'll just write e to the negative 200t cosine of 2000t minus 90 degrees. So that's our function. We don't know if it's a current or a voltage function. This asks us to find the complex frequencies. So our complex frequency is here, right? There's our Neper frequency, there's our radian frequency, and then we have a different Neper frequency, right? But the same radian frequency. So what we have is S1 is equal to negative 100 plus J 2000t. Whoops, just there's no t there. Plus J 2000, right? It's a frequency. But we also have the complex conjugate of that, and we also have our S1 conjugate, which is negative. Well, we'll say that's equal to S2. So that's equal to, it's still negative 100, but minus J 2000t. And then we have an S3, which is equal to 200. So it's equal to negative 200 plus J 2000. That's the 2000. And I'm doing the T again, just 2000, right? And then we have an S4, which is S3 conjugate. So that's our still negative 200, but we have minus J. That's 2000, not 2000t. 2000. Okay, so I think I corrected that. So we have we have four complex frequencies. Well, what about our complex constants? What are the complex constants that we have here? We also then have we'll do it in red, a K. We'll do K12, that complex constant. So that's going to be equal to 1/2 times that 2, right? Times 2 e to the j, and we'll do minus plus 90 degrees because this is 90 degrees, e minus plus j 90 degrees. And if we, yeah, we'll just leave it that. So it's equal to, that's a 1, right? So that's equal to just 1 e to the j minus plus j 90 degrees, where the negative 90 degrees is associated with S1 and the positive 90 degrees associated with S2. And then we're going to have a K34, which since this coefficient is a 1, right? Or this coefficient, we'll look at it down here, is a 1. So that's just equal to 1/2 e to the j. And then, minus plus 90 degrees. So if we're going to write that as a, if this happened to be a voltage, let's say that's V of t, our voltage phasor V34 would equal let's see, our voltage phasor is still going to be 1. It's going to be twice times the K, so it'll be 1 angle minus plus 90 degrees. And this voltage phasor, the two phasors 1, 2 are going to be equal to 2 angle minus plus 90 degrees. All right, so that's for A. So you probably should make sure you pause this and try to solve for B now, where again we're going to try to identify the frequencies, and we'll also additionally look at the complex constants. So here we have we can write this again. This is in cosine form, so we don't have to do the conversion, but we can say this is equal to 2 cosine for t plus phi minus e to the negative 10t cosine for t plus phi. So our S12, right, we're going to have the two complex frequencies associated with our first function here. That's going to be that we don't have a Neper frequency here, right? So that's just equal to 0 plus or minus our J4. And here let's, I was writing T before, so it may help to put in our unit so we don't make the mistake of writing in T. So that's a per second, right? We can write that whole thing as per second. And then our complex constant K, our K12, that's going to be equal to 1/2 times the 2. So we'll write that in, 1/2 times 2, times that 2 there, times our e to the plus or minus e to the plus minus j phi, right? So since we have a plus phi here, before we had a minus 90 degrees in the last one, so here we have plus, so the plus goes on top. That's associated with S1. And then of course our S34, that's equal to negative 10 plus or minus J4, and our K34 is equal to, we have a negative, right? That's negative 1, so it's going to be equal to negative 1/2 times 1, so we'll just do the 1/2. No, we'll do the 1/2 times 1 to make that clear. 1/2 times 1 e to the plus or minus j phi for that phi there. And again, so that if we just look at this one, so that implies if we have our voltage phasor, these are complex constant, that's equal to twice that. So our voltage phasor for 3,4 is equal to negative 1 angle plus or minus phi, right? We drop the j when we're looking at just the phasor. Okay, so the last part here was C. C, we have the product of a sine plus a cosine. When we have a product of a sine plus a cosine, we have to use our trig identity to break that apart. So I'm going to ask you to try that on the worksheet that you have. I'll post the solution for the worksheet, but make sure you can use your trig identity and solve for this. Solve for the frequencies. You should also solve for the complex constants K, and try to solve for the voltage phasor. We'll talk more about if it's a voltage, whatever the phasor is. It could also be a current. All right, so we'll finish up this video here.